Light can give us a picture of the universe at night. We see photons coming from the stars, galaxies, far objects. Photons are the most abundant particles in the universe. But can we see what's going on inside stars? How can we get a glimpse of the unknown? Good news, an uncommon eye is opening up new frontiers.
Why doing astronomy with neutrinos when they are so hard to detect? Well, the reason is simple. First of all, the neutrino has no electric charge, so it's basically the same as a photon, the particle of light. So you're doing the same astronomy. The critical difference between neutrinos and light is neutrinos go through walls, light doesn't. And so the inference is that they may reach us from places in the universe that we have never seen before. So we built IceCube to do astronomy with neutrinos. Now, the simplest way of thinking about astronomy is that you go out at night, you look at the sky, and you see beams of light coming from stars. This is the perfect analogy. IceCube is basically a big eye that looks at the sky, and instead of seeing beams of light, it sees beams of neutrinos. Now, why were we interested in neutrinos? Why not use light? It's cheaper and easier. Well, we are very likely to see very different things. And in fact, at the moment, we have detected our first beams, and we are trying to figure out what we are actually seeing. But educated guesses are that we are seeing very powerful cosmic accelerators, maybe supernova remnants, gamma ray bursts, active galactic nuclei, all the things that are part of the high-energy universe.
What is so special about the South Pole? The South Pole ice itself is the detector. Between 1.5 and 2.5 kilometers below the surface, groups of light sensors are in position to see the light produced by particles passing through the ice. Over 5,160 of these light sensors have been deployed, instrumenting a volume of 1 square kilometer under the ice. High-energy neutrinos produce a zoo of charged particles when they interact with the ice. These particles produce an explosion of light, and IceCube captures it in its sensors. What's critical in the design is how far light travels through the ice. The light sensors have to be spaced according to the absorption length, the average distance light travels in the ice. In tap water, light will travel 2 meters. In distilled water, 8 meters. In ice beneath the South Pole, light travels more than 100 meters. In some places, even more than 200 meters. The ice in the South Pole is one of the clearest solids that exists. It may not be possible to build a solid in a laboratory as transparent as this ultra-pure ice, which, in the end, is just snow that condensed and fell on Antarctica about 100,000 years ago at the depth of IceCube.
About 2 years ago, we were doing an analysis where we were looking for extremely high-energy neutrinos. We actually knew exactly what we are looking for. We were looking for something that's called cosmogenic neutrinos. It doesn't matter what that is. We didn't find any. But when we looked at the data, we found something that we had never seen before. I remember when I was shown these events the first time, and over the years we have looked at thousands and thousands of events on the online display, and I knew I'd never seen events like those two. In fact, they were so special we called them Bert and Ernie. After seeing them, it was clear what was special about these events, and we designed a new analysis that could go and look for more of these. So by now, Bert and Ernie have 26 more friends, which we recently published, claiming that we have evidence for neutrinos that come from space. Where do they come from? That's our next frontier. And of course, everybody has already ideas. We know that some of them are not emitted in the direction of the center or the plane of our own galaxy. So they come from outside the galaxy. There are hints in the data that some of them actually may come from our own galaxy. The problem is there is not enough statistics, there are not enough events to come to a conclusion. So then we started busy approaching a different direction. We started to look for more events. And so I think, I'm afraid you will have to stay tuned, but eventually we'll figure it out. What's next? Well, clearly finding more of these very special events. By the way, what's special about these events is that they have enormous energies. That's why they look different from anything I had seen before. We detect a neutrino every 6 minutes, but they are rather uninteresting and produced in our Earth's atmosphere. These events have 10 times bigger energy. So clearly we want to get more of these, and so what you do is you build a bigger detector. And we are now figuring out how to do that. And it turns out it's not that difficult, because we found out while building IceCube that the South Pole ice is much more clearer than we had guessed. And so this allows us to build a much bigger detector by basically doubling the number of sensors that we have to deploy in the ice. So we are busily designing our next step.